So how many papers do you have about this?
I have actually 0 papers literally about this sequence, but I have somewhere between 5 and 10 papers about problems related to sequences like this.
And how did you hear about this sequence?
From the source itself. I heard about this sequence literally from a talk by Douglas Hofstadter at the Rutgers Experimental Math Seminar. My advisor was Doron Zalberger when I was a PhD student at Rutgers. One of my academic siblings, who was also my office mate at the time, is Douglas Hofstadter's nephew.
Wow.
So he had me in to getting Douglas Hofstadter to come give a talk at his seminar. So this is my second or third year of grad school, and Hofstadter gave a talk about the Q sequence and a couple related sequences, and then Zalberger decided that that would be a good problem for me, and he was right.
Was this in your dissertation?
Most of my dissertation was about sequences like this.
I see, I see. What are some of your results, maybe?
So I'll talk more generally about my results while I show off other people's results.
Right.
So there's a few things you can do to actually prove things about sequences like this. One of those things is to change the initial conditions. So if instead of Q of 1 equals 1, Q of 2 equals 1, you change the conditions to Q of 1 equals 3, Q of 2 equals 2, Q of 1 equals 1. And then you go and calculate terms, you get a very predictable sequence. 3, 2, 1, 3, 5, 4, 3, 8, 7, 3, 11, 10, where every third term is a 3, and then the other terms, every third term goes up by 3 into two interleaved sequences. So it's like 3 interleaved sequences, one of which is constant, 2 of which are linear.
Okay, so we have 3,
so
then
3,
3.
3, 3, and
Okay,
then there'll
okay.
be more 3s, 2, 5, 8, 11, and then it'll be a 14, and then 1, 4, 7, 10, and then it'll be a 13. This is not only empirical, this is really actually very easy to prove. You just do a 3-part inductant argument and it all goes through very easily. This was discovered by Solomon Golomb in the early 90s, and as far as I can tell, the only place that this is actually published by Golomb is in a note in the OEIS that he sent to Neil Sloan.
But wait a second. So here, what is actually the reason that we will have a well understood behavior if we have these conditions?
I don't have any sort of philosophical reason. The reason is that enough terms work that an induction argument goes through.
I see. However, it's interesting that in the Fibonacci case, just 2 conditions are enough, right?
Well, there are some 2-condition things to Hofstadter or other things that give similar solutions, just that wasn't Golomb's.
I see.
Well,
Okay.
the next one I'm going to mention actually has 6 initial conditions plus that whole 0 thing. So if we do this, and then we do, I'm just going to write this as Q of 1 through Q of 6, or 3, 6, 5, 3, 6, 8, you actually get the sequence. So 3, 6, 5, 3, 6, 8, 3, 6, 13, 3, 6, 21, 3, 6, 34. And in this case, we have, again, 3 interleaved sequences, constant 3 sequence, a constant 6 sequence, and then maybe you recognize this other sequence, 5, 8, 13, 21, 34. These are all Fibonacci numbers.
Sure.
Frank Ruski discovered this one, published it, I believe, in 2000, 2001.
So you're saying with these initial conditions, the sequence has a unique property, right? Or
Well, it has a predictable property.
Predictable,
There are
okay.
other solutions
Okay.
with this property. You can get the Fibonacci numbers into a Hofstadter sequence in many different ways, but this was the first way that was discovered.
I see. All right. Any other initial conditions?
Well, there's lots of other initial conditions that do stuff like this or do some semi-predictable stuff, but the last thing I want to say is actually a different kind of thing you can do, which is change the recurrence. Let's say instead of the Hofstadter recurrence, we change it slightly. I'm going to change the letter to C so it doesn't get confused with Q. So the first piece of the recurrence is exactly the same, but then we insert this innocuous-looking -1 into the second term. And let's say we use the same initial condition, 1, 1.
Okay.
And then we do the same calculations we did for Hofstadter, we get this sequence. 1, 1, 2, 2, 3, 4, 4, 4, 5, 6, 6, 7, 8, 8, 8, 8, 9, and this time it's monotone forever. And except for 1, which appears twice. The number of times that n appears is you write n in binary and look at the number of zeros at the end and add 1 to that.
Wow.
So like all the odd numbers except for 1 appear once because there's no zeros at the end of their binary representation. 4 appears 3 times because it's 1, 0, 0 in binary. So there's the 2 zeros, and then you add 1, it appears a 3rd time. And so on. So like 8 appears 4 times, 16 will appear 5 times.
So you're saying we just added this extra -1 in the second parenthesis, right?
Yeah. I changed the name to C for the name Conolly because it's not Conolly sequence. And we can prove that this happens. And in fact, there's a combinatorial interpretation of such sequences. It's a little more complicated than I can get into in this video. Yeah. But it involves an infinite tree where you do a pruning operation and count leaves in this tree with certain labels.
Wow.
So there's actually combinatorics and trees underlying this thing, and not any of the other stuff I talked about.
That makes sense because it has more symmetrical structure with this, right?
In a sense, right. And essentially what this boils down to is enumerating the leaves with certain labels in the tree. This ends up counting left children, and this ends up counting right children in a complete binary tree.
That's insane. Thank you.